In this video, we're going to go through the three examples that you find there in Chapter 6 of Dynamic Response. The first example here is a first order system, y dot plus 5y is equal to 10 u of t, where our input here is a linear function in time, and we know the initial value there for y. So what we'll do is take our Laplace transform of the equation of motion, so you get s times y minus initial value for y plus 5y is equal to 10 times the Laplace transform of our input there of u. So from this I get s plus 5 times y, left hand side. The right hand side I have 10 u of s plus the initial value for y, and then solving then for the Laplace transformed response y of s, I get 10 over s plus 5 u of s plus the initial value for y divided by s plus 5. And so since we are given our input here as being 5 times the linear function in time, the Laplace transform of that is 5 over s squared. So in the end, what I get here is 50 divided by s squared, s plus 5, plus, again, initial value for y divided by s plus 5. So what we have here is the first term in here is coming from what we've been calling the forced response. And this is coming from the free. Definition is such that, again, the free response is what you get when you turn off the forcing, and the forced response is when you set your initial conditions equal to 0. So from our what we know about doing our inverse Laplace transforms, we get partial fraction expansion of the first part of a1 divided by s squared, a divided by s. Those two terms are there because we have that repeated root of s equal to 0. And then we have a third term due to the s equal to minus 5 root. The free part, that's going to be a4 divided by s plus 5 as that. So if we find the inverse Laplace transform of y of s, inverse Laplace transform of 1 over s squared is just a t, so that's a1t. a2, that's times the step function h of t. a3, inverse Laplace of s 1 over s plus 5 is e to the minus 5t, and then a4 also e to the minus 5t. So what we can see from here is that our forced response was really embedded in our first three partial fractions. Okay, and our free response gave rise to that fourth term there. But once we look at the response, we see that the long time response, the steady state, is only the first two. Whereas the last two are transient. They die away with time. So I think here is a good example where you can see that the definitions that were given in this lecture and the difference between forced free classification and the steady state and transient is that the forced part will produce not only steady state terms, but also transient terms. So this gives this plus that. Where the free response always gives rise to these transient terms. So again, make a clear distinction between the forced part, which comes from everything but the initial conditions. That will give us steady state terms some of the times and transient terms, where the free part always adds to the transient part. So the question that we might have here, related to some of the other points made in lecture, is does the final value theorem apply here? And there's two ways we can look at this. One is that we can simply look at S times Y of S. What has to be true about that? What has to be true about the poles of S times Y of S? Do we meet those criteria? Or another way to look at that is just look at the response. Look at Y of t. What is Y as t goes to infinity? So think about this, compare and see why in this case you know the final value theorem does not apply. You can just know, once you know the answer, you see why that's true. But the way that you would know this in advance without actually solving the problem is you have to look to see what criteria must be met in order for the final value theorem to hold true. The key to all this really comes back to this term here. There's a growing term in time there, and that came about from this term here. Does that meet the criteria for the final value theorem? Now let's look at the example there on page 3. Page 3, now we have a second order system, and we have, for input, we have another step function, h of t, and we are given some initial conditions on y and y dot, and what we want to do again is look at the difference between the forced and the free part and what is the final response. So if I take a Laplace transform of that, I get s squared y minus s times the initial value for y minus y dot initially. I have 4y of s, oops, left off a term, 4 times s y minus 4 times the initial value for y plus 3y. And the right hand side I've got 6 times the Laplace transform of our input u of s. So I have s squared plus 4s plus 3 all times y. On the right hand side I have my Laplace transformed input times 6. I have s times the initial value for y. I have 4 times the initial value for y, and I have the y dot initial like that. So y, therefore, the transformed response y is equal to 6 divided by s squared plus 4s plus 3, Laplace transformed input u of s, and then I have my second term, which is s plus 4, initial value for y plus initial value for y dot, again divided by s squared plus 4s plus 3. In this case, our input is the step function, so the Laplace transform of that is 5 over s. So this is a 30 s, and then I factor out my s squared terms and get s plus 1 times s plus 3 plus the same thing here, s plus 4, initial condition on y and y dot like this. S plus 3. So, how do we classify these? Well, this term there produced this, so this is the forced response. That's the part you have with the zero initial conditions, and this gives us our free, because that's what you have when you set the input equal to a 0. Then we go through a process then of factoring, doing a partial fraction expansion, I should say. I've got a1 over s. Since I have distinct roots, I can write this as a2 s plus 1, a3 s plus 3, and then have a4 s plus 1, a5 s plus 3. So at this point, whenever, in fact, let me take this one more step, a1 divided by s. Since I have s plus 1 in both those terms, I have a2 plus a4, whatever factors you get for that, s plus 1, and then a3 plus a5 divided by s plus 3. So in the end, when I take the inverse Laplace of y, I get a1 ht plus a2 plus a4 all times e to the minus t, that a3 plus a5 e to the minus 3t. So somewhere along the line, some of our terms got mixed together in the sense that the forced part really is all of these here. So this is forced, and this is free. But note that in the next line down, some of the terms for this first term came from there and from there, just like this here is a mixture of these and these. So at this stage we see, well, we can no longer distinguish between free and forced. The real question at this point is what is long-term and what is transient. This is a transient. It decays away. Where this is a steady state term. So again, at the beginning, it makes sense to talk about forced and free, but if you're just strictly looking for the answer, then some of the forced terms end up in the steady state part, some in transient. The free response is always going over into the transient part. So keep clear that the distinction between forced and steady state and free and transient. Let's look at the third example. Third example here is on page 5. So here we have another second order system. I think I failed to write this down, so let me just say that y and y dot initially are a 0, just for the sake of working out the example. So with that, when I take the Laplace transform, I get s squared plus 4s plus 12 times y. The right hand side, I get 4s plus 3 times u. U being the Laplace transform of our input. So therefore, the output transform, 4s plus 3, s squared plus 4s plus 12, u of s. U of s here is equal to 5 over s. So when we look at our poles, we see that we have one which is a 0. The other two, when I set s squared plus 4s plus 12 equal to a 0 to find poles of the transfer function, I get p1, p2 is equal to minus 4 plus or minus 4 squared minus 4 times 12, all divided by 2. And those two poles are minus 2 plus or minus 2 square root of 2j. Is that. So therefore I can factor things. I can write y of s then is equal to a1 divided by s, a2 s minus p2. I can do this because I have distinct roots. However, since our roots are complex, they're appearing in complex conjugate pairs, we know that we don't have to reevaluate this one. We just take the complex conjugate of the one there for a3. So we get a1 over s. Get 2 times the real part of a2 divided by s minus p2. So we're in a position now where we can say that y of t then, inverse Laplace of y, is a1 h of t, the step function, plus 2 times the real part of the inverse Laplace transform of a2 over s minus p2. That's a2 e to the p2t. That's complex, but we pull off only the real part. And so what I'm going to get here is 2 times e to the minus 2t. And some coefficients here, a and b, which I don't really need to find to draw the conclusions I need to. I mean, you can always go through the process of finding a2 up here, multiplying out, keep only the real part, and whatever is left is a and b. But the one I really want to look at here is a1. So our rule here for the partial fraction expansion says for a1, I multiply s times y of s, and set s equal to a 0 in this case. So this is s times, or s divided by s minus p2 s minus p3 and in the numerator, what did I have here? I had a 4s plus 3. And keep in mind that this number here, this multiplies out to be s squared plus 4s plus 12. Maybe that's an easier way to write that, because whenever I set s equal to a 0, my s's will cancel out here. That s is gone, this s is gone, that s is gone. And so if I've done things right, which I haven't, I think I've left off a 5 somewhere here. There was a 5, so this gets multiplied by 5, and therefore there's a 5 here. I think my numbers are wrong here, but let me multiply it through and everything. Let's make sure that I get it. There's 3 times 5 divided by 4. Yeah, that's right. This is a 5/4. So this is what A1 is right now. I'm not really caring about A and B because I'm wanting to sort of check and verify that the final value theorem is going to work. So the check here is based on the final value theorem. We know final value theorem applies since s times y of s has poles only in the left half plane. And we verify that right here. If I take y of s times s, that s will cancel out, and we see that the poles therefore are here with a negative sign. So it's on this basis that the final value theorem applies. So I can do that. We know the final value theorem says that the final value, the value of y as time goes to infinity, is the limit as s goes to a 0 of s times y of s. And so again, y of s was equal to 5 4s plus 3, all divided by s squared plus 4s plus 12, limit. S cancels out, s, and so again I'm left here with 5/4. Well, we see that from our solution. We had that y of t was equal to a1 h of t plus the 2e to the minus 2t with some cosines and sines. This is a transient term. So that goes away. So we can see here the steady state value is that. The steady state value is equal to a1, which is 5/4, and that's exactly what we got there. So the point being is that if you carry through with all your inverse Laplace transforms, you separate out your steady state transient part, then you can see that the final value theorem, provided that it applies, should provide you a check with that. You just apply that theorem, and again, if it applies, you should get the same steady state value from that as you do from the solution.